Hi, I'm Mark Bryssamian. In this video, we'll start an introduction to set theory with some basic definitions and some examples involving simple sets and then a kind of proof that's called the element method of proof. Set theory is one topic in our course that you might have some familiarity with. The idea of sets, elements, subsets, unions, complements, etc. That's all stuff that you've probably seen before, certainly seen before. But there is actually some subtlety in the subject of set theory, a lot of subtlety. So you might find that you become confused about things that you did not previously find to be confusing at all. For one thing, it's important to realize that the words set and element are actually undefined terms in set theory. You might think that you know what those words mean, but you don't really. For instance, think about a definition for the word set. It could be something like this. A set is a collection of things called elements. But then what's a collection? You've got to either provide a definition of collection, and of course that definition could not include the word set in it, otherwise it would be what's called a circular definition. So you've either got to come up with a definition of collection or just admit that collection is undefined. In that case, the definition of the word set would really just be saying that the words set and collection are just declared to mean the same thing, but that thing is, well, it would be undefined. So that's the kind of thing that's confusing about set theory for students who haven't before encountered this idea in math that you can have a subject where certain words are what are called undefined terms. So it's important then when you're studying set theory to be as clear as possible about what terms are undefined and what terms are defined. But for our purposes in Math 3050, we won't really need to deal with the idea of undefined terms beyond the confusing stuff that I mentioned earlier. But be aware that the subject of set theory is actually much more subtle than you might realize. Now, in this video, I'll be presenting definitions in a different order from the book in order to give some more precise definitions for set terminology, more precise than the definitions given in the book. So to begin with, I'll introduce the idea of the universal set. The author doesn't introduce this idea until a few pages into the section. I find it's useful to discuss it first because it allows us to make some more precise definitions of other set theory terminology. So here's what the book says about the universal set. Most mathematical discussions are carried on within some context. For example, in a certain situation, all sets being considered might be sets of real numbers. In such a situation, the set of real numbers would be called a universal set, or a universe of discourse for the discussion. So that's all kind of vague, but we'll have a symbol for the universal set. We're going to denote it by the letter U. The next thing I want to talk about is set equality. It's common for authors to define set equality in terms of subsets. Our book author does this on page 379. But I feel it's very important to introduce the idea of set equality before the definition of subset in order to realize that set equality is a simpler and more fundamental concept. Here's my definition. So this symbol is spoken A equals B, and the usage is A and B are sets. So what I mean by this idea of usage is that, of course, you've seen symbols like that before in math. X equals Y, most often in the past has referred to real numbers, X and Y. So that equation, X equals Y, means something when X and Y are understood to be real numbers. But what I'm saying here is, if you write this symbol, A equals sign B, and A and B are sets, then that symbol means something different. What it means in that setting is that A and B are sets that have the same elements. Another way of saying this is that regardless of the element X that's chosen from the universal set U, the statements X is an element of A and X is an element of B will either both be true or they'll both be false. Now I'll finally get around to the definition of subset, which our author does earlier in the section before those previous ideas of the universal set and set equality. This symbol is spoken A is a subset of B. And when you use that symbol, A and B are sets. And here's what it means. For all x in A, x is in B. So that's the meaning stated as a universal statement. Now, the meaning can also be stated as a universal conditional statement. Here's how it would read. For all x in the universal set, if x is in A, then x is in B. So in the book, this definition of subset comes before the idea of the universal set. And so the author does not actually present a formal definition or a formal version of the definition of subset. The author does not present these kind of quantified statements in their definition of subset. Now, another kind of subset is what's called a proper subset. The symbol for that is this. I'm going to write that a little larger. That symbol is spoken, A is a proper subset of B. And what it means is this. A is a subset of B, and A is not equal to B. So there again you see another reason for introducing the idea of set equality earlier is that we can have this kind of definition of proper subset. And we can have this formal presentation of that. The meaning of A is a proper subset of B is this. A is a subset of B, and A is not equal to B. Now I want to talk about notation. It would be really natural to use this symbol for subset and this symbol for proper subset, analogous to the inequality symbols, less than or equal to and strictly less than. But there's a problem with that in that some books use this symbol to denote a subset, not a proper subset. So since there's a possibility of confusion, we really don't have any choice. We have to just not use that symbol. So I'm going to use this symbol for subset and this symbol for proper subset in these notes. You'll notice that in the book, they don't even have a symbol for proper subset. So the book acknowledges the problem with this as a possible symbol. They acknowledge that basically by ignoring it and just not mentioning it. You really can't use this symbol because it's been made ambiguous because some people use that to denote subset. Some people would like to use that to denote proper subset, so we just can't use it for either. But the takeaway from that is that in the future, when you're reading papers or books and this symbol is used, you have to be aware that you have to know in what sense the author is using that symbol. In some places, this symbol will be used to denote subsets, general subsets. And in some cases, the same symbol can be used to denote proper subsets. So you've got to make sure when you read math, if you encounter that symbol, that you pay attention and keep track for yourself of how that symbol is being used. All right, now I want to talk about proving and disproving statements that use the terminology of subsets. So first of all, what does it mean to say that A is not a subset of B? Well, we can work through that using the formal definition. The formal statement of the definition of subset is this, the one that we will mostly focus on. For all x in the universal set, if x is an element of A, then x is an element of B. So with that formal statement of the definition of subset, we can grapple with this. What does it mean to say that A is not a subset of B? Well, to start with, we just write that formal expression for A is a subset of B, and we park a negation in front of it. So there's our formal expression of this, that A is a subset. So we've formed the negation the cheapest way just by parking the negation symbol in front. Now, we've run across this idea before. When you park a negation in front of a quantified statement, it's clear if you can then rewrite that statement with the negation moved to the right. So we'll move the negation symbol one notch to the right past that universal quantifier. So when we do that, the universal quantifier changes to an existential quantifier, and the negation ends up parked in front of the predicate. Now, remember that the negation of an if-then statement is a new statement that is not an if-then statement. It is an and statement. So there's our and statement, and then we can simplify this. The negation of x is an element of b is just simply x is not an element of b. So there, to say that a is not a subset of b means this. There exists an element x in the universal set such that x is an element of a and x is not an element of b. Let's go on. Example 1. This is similar to 6.1 number 4. Let A be this set, and let B be this set. Prove or disprove this, that A is a subset of B. Well, first thing we have to do is we have to figure out whether we believe this is true or false. If we believe it's true or false, then we have to think about how we're going to prove that it's true or false. That'll come next. But first we have to figure out which we think it is. So let's figure out what's in set A and what's in B. First of all, let's build some numbers that are in A. So some numbers of that form. So you see, just by exploring, we get an idea of what the set A looks like. We can write the set down now. So A is an infinite set, looks like that. Now, I'm not going to go through this kind of process again to explore to figure out what B is. I think you can see what B is going to look like. I'm just going to write down the result. That is the description of B and the description of A. Now let's go back to our statement that we're supposed to prove or disprove. The statement is A is a subset of B. So looking at these sets, it does seem like every number that's in set A is in set B. That 5, or that negative 5, that number 1, that number 7. So it seems that that statement is true. But now we have to turn our attention to how do we actually prove this. Now this brings us to what's called the element method of proof. We want to prove that A is a subset of B. But that means that we have to prove this. We have to prove that this universal conditional statement is true. So we'll do that on the next page. So that's the thing that we want to prove, this great big universal statement. So we will use the direct proof. So there's how the direct proof starts, as always. We write down a generic particular element, one that is in the domain and satisfies the requirement mentioned in the hypothesis. X is an element of A. We have no choice but to start our proof that way, because we're proving this universal conditional statement. Furthermore, we have no choice about how our proof has to end. It has to end with this. X is an element of B. So we can skip down to the end and put that in as the last statement of the proof. So there's the frame of our direct proof. Now, we've done this kind of thing many times before. Notice that in the first statement, there is a defined term. X is an element of A. So we have no choice but to follow this statement up with a new statement that unpacks that definition. So there we've unpacked this statement. To say that X is an element of A means that X can be written as 6. I'm going to say 6k minus 5 for some integer k. Now let's look forward to the end of the proof. We have to end with this, and so we have to precede that statement with a statement about what that really means. So if we want to end the proof with the statement that X is an element of B, we have no choice but to have at some point before that proven that X can be written this way. So there's the gap that we need to bridge. Well, so our goal is to have an equation with an X on the left side and 3m plus 1 on the right side. But look, we've already got an equation with X on the left side and 6k minus 5 on the right side. So let's just work with that equation. We already have the X on the left side. Let's work on rewriting the right side. We want to have a 3m plus 1 on the right side. So watch this trick. Instead of saying 6k minus 5, we can just say 6k minus 6 plus 1. That's a trick. But look, then we can do this. And once we can do that, we can rewrite that further. So there we are. We have X written as 3 times some stuff plus 1. We want to be able to say that X equals 3 times some integer m plus 1. So now it's very clear what we should do. We should introduce m to be this. So now we've bridged that gap. So we can number our unnumbered statements. And there we go. So you see that we just did a standard direct proof of this universal conditional statement. The direct proof structure gave us the beginning and ending statement. And then we had no choice about the statements following the first statement and preceding the final statement. And this particular instance of direct proof is, in the setting of set theory, is what's called an element method of proof, because you're talking about a proof involving elements of sets. Let's go on. Prove or disprove. B is a subset of A. Well, let's go back up and look at our sets A and B. To say that B is a subset of A would mean that every element of B is also an element of A. Well, we see that doesn't seem true. I mean, we can see some numbers that are in B that are not in A. So we know that the statement that B is a subset of A is not true. So how do we prove that? So we see that B is not a subset of A, but now how do we prove it? Or how do we disprove that B is a subset of A? So we want to disprove this. And the negation of that is the following. So if we want to prove that B is not a subset of A, all we have to do is come up with an example of an X in the set U such that X is in B and X is not in A. Well, that's easy. Just give an example. So if we let X be the number 4, then X is a number that's in B and is not in A. So we can say that this number 4 is a counterexample that shows that this universal statement is not true. Or you could say that it's an example that shows that this existential statement is true. So either way, it's an example that proves that B is not a subset of A. Now I want to go back to the idea of set equality. Remember that we defined it before we had the idea of subsets. Set equality was defined this way. The sentence that A and B are equal means that A and B have the same elements. That means that this statement, X is an element of A, and this statement, X is an element of B, will either both be true or they'll both be false. Well, now that we have the notion of subsets, we can rewrite our definition of set equality. We can give a formal presentation this way. For all X in the universal set, if X is in A, then X is in B, and if X is in B, then X is in A. That's what it means to say that the sets have exactly the same elements. Oh, but we have abbreviations for these symbols. It's this. And this is abbreviated this way. So set equality can be abbreviated this way using subset notation. To say that A equals B as sets means this. A is a subset of B and B is a subset of A. Now I want to talk about operations on sets. The union of A and B is this set. The set of all X in the universal set such that X is in A or X is in B. The intersection of A and B is the set of all elements such that X is in A and X is in B. The complement of A, denoted this way, is the set of all X in the universal set such that X is not an element of A. And finally, the set difference, this symbol, B minus A, is the set of all X such that X is in B and X is not in A. That can also just be written this way. It's the set B intersect the set A complement. So for our second example, I want to do an exercise similar to 6.1, number 35. A is this set, B is this set, C is this set. We're supposed to build this set. Well, to do this problem, you have to remember some old terminology from back in chapter 1. This symbol is spoken B cross C, and it means the Cartesian product of B and C. And remember what that means. It means it's the set of ordered pairs of the following form. So it's the set of ordered pairs of the form little b, comma, little c, where little b is an element of set capital B and little c is an element of set capital C. So it's this set of ordered pairs. So the elements of B cross C are these ordered pairs. Now we're supposed to build this, A union that. So A union that is going to be a set. So we put set brackets. Now what does that consist of? It consists of all of the elements of the universal set that are elements of A or that are elements of B cross C. So let's see, A only has one thing in it. So we put that thing in. And then B cross C has all of these things. So let's just grab all those, copy them, and move them down. So there is A union B cross C. Let's go on. Now we have to find this, A union B cross C. Okay, well for that we have to find the union of A and B first. So there's A union B. Now we have to cross that with C. Now remember what the cross product is. It means the set of ordered pairs. Each ordered pair is going to have one of these things on the left and one of these things on the right. So there you see that the set A union B cross C looks very different from the set that we did earlier. A union B cross C is this thing, this set that has 4 ordered pairs and also just the number 1 by itself. And the ordered pairs are all of the type either the letter U or the letter V on the left, and the letter M or the letter N on the right. Come down and look at this set. This set is just a bunch of ordered pairs. There are no separate single things in it, like the number 1 sitting by itself. And furthermore, the ordered pairs on the left sides of the ordered pairs, there can be 1s or U's or V's. So the moral of this is that when doing set operations, you have to be careful. You don't have the idea of associativity. These symbols were exactly the same except for the placement of the parentheses, and you see that they denote completely different sets. Let's go on. Now, to determine complements of unions, intersections, and differences, we have to use the formal presentations of the meanings of those sets. And those formal presentations involve and or statements. And so negations of and or statements involve using De Morgan's laws. So for example, find A intersection B complement. Well, remember what that means. The complement of a set is the set of all x in the universal set such that x is not an element of that set. So let's go from that most basic definition. So there you see that the complement of A intersection B is the union of A complement and B complement. And we used a bunch of things here. First of all, notice that we used the definition of complement twice. We unpacked the definition at the beginning and we packed it up at the end. And we used the definition of not an element of twice. We unpacked this symbol at the beginning and we packed it back up later. We used the definition of intersection and so forth. And in the very middle, we used De Morgan's law. Now, you actually have an exercise in one of your homeworks that's something like this. What does it mean to say that x is not an element of A intersection B? Well, what it means is this. So, your homework exercise would basically amount to these steps here that are part of this larger calculation that I just did. Okay, let's go on. I want to talk now about what's called the empty set. This symbol, which is spoken phi or phi, P-H-I, a Greek letter. It's the empty set. It's the set with no elements. Let's do some examples about this. So, for instance, all these examples or parts of this example are similar to questions that are asked in 6.1, number 18. Well, some of them are. Is the number 0 in the empty set? Well, no, because the empty set has no elements. Okay, question B. Is the empty set equal to the set containing the empty set? Well, no. The thing on the left is a set with no elements. The thing on the right is a set that has one element. So those two things can't be equal. How about this? That symbol. Now that symbol is read, the empty set is an element of the set that contains the empty set. Well, yeah, that's true. What about this symbol? Is the empty set an element of the empty set? Well, no, the empty set has no elements. Now, this question is about a fact that you may have heard before, but may have not understood or not known how to prove. The statement that we have to prove is the empty set is a subset of every set. Now let's give that statement a name. The empty set is a subset of every set. And let's write it formally. So the empty set is a subset of every set. Notice this is confusing because the quantifier is at the very end. So I'm going to put the quantifier in front. The statement that the empty set is a subset of every set can be written formally as this. For all sets A that are subsets of the universal set, the empty set is a subset of A. Well, the key to thinking about how to prove statement S is to think about the negation of statement S. If S is true, the negation of S would be false. On the other hand, if S is false, the negation of S would be true. So let's look at the negation of S and see if we can figure out how to prove it's true or how to show that it can't be true. So the negation of that universal statement for every set A, phi is a subset of A, would be this. There exists a set A such that phi is not a subset of A. Now here it's useful to remember what we did a while ago. We wrote what this really means. What does it mean to say that some set is not a subset of some other? Let's go back and look at that. What does it mean to say that some set is not a subset of some other set? It means to say that A is not a subset of B means that there's an X in the universal set such that X is in A and X is not in B. That's what it means to say that A is not a subset of B. So to say that the empty set is not a subset of A would mean this. There'd have to be an example of an X that's in the empty set and that is not in set A. But the empty set doesn't have any elements, so there's no way that you're going to find an X that's in the empty set and that's not in set A. So we see that negation of S cannot be true. So since negation of S cannot be true, we conclude that S is true. So the empty set is a subset of every set. Now finally, question F. Is the empty set a subset of the empty set? Well, yeah, we just proved that. Okay, let's go on. Now I want to talk about disjoint sets, mutually disjoint sets, and partitions of sets. Two sets are called disjoint if their intersection is the empty set, and a whole collection of sets is called mutually disjoint or pairwise disjoint if, when you look at any two of the sets in the collection, their intersection is empty. So if the collection has indices and you look at two sets that have different indices, then they're disjoint. And then finally, a finite or infinite collection of non-empty sets is called a partition of a set A when A is the union of all those sets and all of those sets are disjoint. So for example, is this a partition of the set of real numbers? So this is the set of positive real numbers and this is the set of negative real numbers. Well, notice those two sets are disjoint. So that's one of the requirements for being a partition. But the other requirement is not satisfied. The union of these two things is not all of real numbers, because this union is missing the number 0. 0 is neither positive nor negative, so it's not in either one of those sets, so it's not in the union. So this is not a partition. We failed this part of the definition of partition. Let's go on. Is this a partition of the real numbers? The integers and the rational numbers? Well, no. For one thing, those two sets are not disjoint. So for instance, the number 5 is an integer, and 5 is also a rational number, because 5 can be written as 5 over 1. And also, the union of those two sets is not the set of all real numbers. For instance, the number pi is a real number, but it's not an integer and it's not a rational number. So we flunked both tests for partition. The sets z and q are not disjoint, and their union is not the set of all real numbers. Let's go on. Is this a partition of the integers, even integers and odd integers? Well, yes. The reason is when you write down the definition of even integers and the definition of odd integers, you realize that those two sets are disjoint, and their union is the set of all integers. Now, how do we know both those things? Well, it's from the quotient remainder theorem. The quotient remainder theorem says, the quotient remainder theorem using d equals 2 tells us that for every integer n, either that's true or that's true, one or the other, but not both. So the quotient remainder theorem tells us that this collection of sets is a partition of the integers. Finally, is the set of prime numbers and the set of composite numbers a partition of the set of integers? Well, no, because remember, prime numbers and composite numbers are numbers that are greater than 1. So all the integers that are less than or equal to 1 are neither. So these sets are disjoint, but their union is not all of the integers. So for instance, the number 1 is neither prime nor composite. The number 0 is neither prime nor composite. The number -5 is neither prime nor composite. So we flunked the test for being a partition because we flunked that. The union of prime and composite numbers is not all the integers. So not a partition. Now I want to talk about unions and intersections of an indexed collection of sets. So you can have unions of a whole bunch of sets by just putting a symbol in front that's a great big U symbol and a description of the indices that describe the sets that are in that union. And that description of indices can be a finite list like that, or it can be a list that goes on forever like that. So what this would mean, the union of an infinite collection of sets, would mean this. The set of x's in the universal set such that x is in at least one of those sets in that union. The intersection of an infinite collection of sets would mean, well, the set of elements of the universal set such that x is in every one of those sets in that intersection. So it sort of means the obvious thing. So for our last example, I want to consider this collection of sets, D subscript I, which are these closed intervals from negative I to I inclusive. So we're going to find various unions and intersections. So this is a finite union. So it's that union. So when you write down the descriptions of those sets, you realize that this union is just going to be the biggest one. In other words, it's just going to be D subscript 4. Now what about the intersection? Well, the intersection is going to be the smallest one. The only numbers that are in all 4 of those sets are these, which is just D1. Now here's a question. Are those sets mutually disjoint? Well, no, none of them are disjoint. They all, every one of the sets of that form contain the number 0. Wait a minute, what is D subscript 0? So D subscript 0 is the set that only contains the number 0. So most of the sets on that list look like these intervals where the endpoints are not just a single number. But one of those sets is just the number 0. But the thing is, these are not mutually disjoint because every one of those sets contains the number 0. Okay, what is this union? Well, that's a more general case of what we did in question A. In question A, we found the union of the first 4 was just the largest. So the union of the first n would just be the largest. And question E, what's the intersection of the first n? Well, that's going to be a generalization of what we did in this one. The intersection of the first 4 was just the smallest one, D1. So it doesn't matter how much farther we go, the intersection of the first n would be the same thing. Okay, what's this? The union of all of them. Well, that's the set of all x's that's in at least one of those intervals. That's going to be the set of all real numbers. And the intersection of all of those from 1 to infinity is going to be that one. Now here's a tricky thing. What about this? If I take the intersection over all I starting with I equals 0, then I've got that set thrown in. And in that case, the intersection is going to be just that set, the set whose element is the number 0, and that's D subscript 0. Well, that's the end of that example, and that's the end of the video. Thank you.